Today we are going to learn how to identify reaction types. So we have 5 types of reactions generically. There are more, but for standard chemistry purposes, we're going to break them down into 5 categories: synthesis, decomposition, single replacement, double replacement, and combustion. So these names sound difficult, but they're not too bad. The only thing that's a little tricky is that sometimes in chemistry we don't always make things easy, and instead of calling it single replacement, it's often called single displacement, but they're the exact same thing. Same thing with double replacement or double displacement. Let's start with a synthesis reaction. If we are looking at a synthesis reaction, in a synthesis reaction, we see that 2 different reactants come together to form a single product. Right, so if 2 reactants are coming together to form a single product, all right, let's look at an example of this. Let's say that we have Mg and O2. When those 2 come together, they will form a single product. So remember that in a chemical reaction, bonds have to break, atoms have to rearrange, and we have to make something new. So the only way that we can put magnesium in and oxygen in is to make them come together to form a single product. Mg is going to connect with O. Now, it's really tempting to put a 2 here at the end of the O, but remember that subscripts are only used for stability. Mg is +2 and O is -2. So the only way Mg and O will ever be stable or happy together is with 1 magnesium and 1 oxygen. Now, I am going to get rid of those charges, and we do have to make sure that we balance the equation. When we balance the equation, we're going to add our coefficients in. You can make your list underneath, but this would be our correctly balanced equation. Now, an easy way to think about a synthesis reaction is in generic terms of A's and B's. If I have some element A and some element B, every time I have a synthesis reaction, they're going to come together to form a compound where the atoms are now bonded together, and that compound will be AB. A synthesis reaction will follow this generic pattern every single time. If we move on to a decomposition reaction is exactly the same as a synthesis, just reversed. So in a decomposition reaction, a single compound is going to break down to form 2 or more products. So it's essentially the reverse of a synthesis reaction. And if you think about what decompose means in your everyday life, decompose means to break down, and it means the exact same thing here. An example of this would be something like hydrogen iodide. Hydrogen iodide is a compound. The H and the I are bonded together. But in a decomposition reaction, that is all we're going to start with. 1 single reactant, and that single reactant is going to break down to form 2 or more products. So the only thing it can break into is H and I. But remember that H is a diatomic molecule, so it only exists as H2. Iodine is also a diatomic molecule, so it will only exist as I2. There are 7 different diatomic molecules. Those 7 diatomic molecules are H2, N2, O2, Cl2, F2, I2, and Br2. When any of those elements stand alone, we need to have 2 of them bonded together. Now that we have both of our products stable, again, we need to show the conservation of mass through balancing, so I would need to put a 2 out front in order to give me the same number of hydrogen atoms on both sides and the same number of iodine atoms. If I wanted to write a generic pattern for a decomposition reaction, the way I'm going to recognize it is that it always starts with a single compound. So there's only 1 thing on the reactant side, and that 1 thing is going to break down to form 2 or more products. So if you notice, it's pretty much the opposite of the synthesis reaction that we saw above. Next, we're going to move to a single replacement reaction. In a single replacement reaction, or again, single displacement, they both mean the exact same thing. In a single replacement reaction, you are going to be able to recognize this because in a single replacement reaction, it is the first type of reaction we see in which we start with an element and a compound, not just one or the other. So we have an element and a compound as our starting material. Basically, the element and the compound, the element is going to come in, kick one of the elements out of the compound to make a new compound and a new element. Again, the key to all of these reactions is that you have to make something new. Your product needs to be different than the reaction you started with, the reactant that you started with. All right, in a single replacement reaction, let's look at an example. The easiest way to identify this is, let's say that we have magnesium reacting with potassium iodide. All right, if you are trying to distinguish between an element and a compound, every time we have a new element, it will start with a capital letter. So here, capital M, lowercase g means that this is just a single element. But here, I have a capital K and a capital I. That's going to indicate that I have two elements bonded together, or a compound. Now, when I'm trying to figure out what it is that I'm going to make, the easiest way to do that is to identify charges and really pay attention to those. Magnesium, when it's in a compound, will carry a +2 charge. Potassium in a compound will carry a +1 charge, and iodine will carry a -1 charge. Essentially, what's going to happen is that our atoms are going to rearrange, but when they rearrange, we need to A, make something new, and B, make sure that whatever it is that we made is still happy or stable. So, magnesium and K can never pair up together because magnesium and potassium both have positive charges. The only two things that can ever pair together are a positive and a negative. So I'm going to take my Mg and I'm going to partner it with my I. Now, stability is always first and foremost, so we need to check to see if this is stable. I paired up the Mg and the I, but the only way they're going to be happy together, or zeroed out, is by finding the lowest common multiple between them, and I know that I'm going to need 2 iodines for every 1 magnesium. So don't forget that whenever you write a new product, you are going to have to make sure that that product is stable. My Mg and my I came out, but I need to show what happened to the K. K instead is going to be standing alone. When K stands alone, it's not diatomic, it's not one of those 7 elements that we listed before, so we don't need to put a little 2 here to be stable. Remember that we only have to worry about charges balancing out when we have a compound, 2 or more elements connected together. If we have a single element standing on its own, we do not need to worry about charges. After you have everybody stable, again, we still have to balance these equations using coefficients to show the conservation of mass. So I am going to put a 2 in front of my K and a 2 in front of my Ki and a 2 in front of my K. If you're not sure on the balancing part of it, check out my earlier video that goes through balancing equations and how and why we do that. All right, with a single replacement reaction, you may need to use your activity series in order to determine if the element is essentially strong enough to kick the other element out of the compound. If you're looking for a general reaction scheme, you will see that you have some element A and some compound BC. Those will rearrange in order to make something new, and when they make something new, the A and the C will pair together, and B will be standing alone. Now, don't forget that when you pair the two together, you have to make sure that you have 1 positive and 1 negative in the ionic compound. A double replacement is going to involve 2 compounds. That's going to be the easiest way to identify that you have a double replacement reaction. So if I have Na and I reacting with MgO, those are both stable and happy. I've already made sure that their charges balance. And now I need to predict the products. Again, I'm really going to focus on charges here. I know the charge of sodium is +1 and iodine is -1. Magnesium is +2, oxygen is -2. Right now, those compounds are zeroed out or happy, but they're going to rearrange partners to make a new compound. So I'm going to start with the Na. Remember that we always write the positive first in a compound. So I'm going to pair Na, which carries a +1 charge, with another element, a new element, no longer with the I. But my only option for a new element here is O, because O is the only other atom that carries a negative charge. So you're going to have to put your positives with your negatives. Then I'm going to have to make sure that my charges balance out. So 2 and 1 fit evenly into 2. That tells me I'm going to need 2 sodiums for every 1 oxygen. You have to make these atoms stable before you do anything else. Then we're going to need a second product. In the second product, we again are going to pair a new positive with a new negative. This is going to leave my iodine and my magnesium to pair together. But again, make sure that you always write your positive charge first. So magnesium first, iodine second, and in order for this to be a happy stable compound, we are going to need to have 2 of the iodines. When you are done making everybody stable, predicting your products, you are always going to need to balance your equation to show that conservation of mass. So I'm going to put a 2 in front. And again, if you're not sure on balancing, check out my earlier video for an explanation. All right, so if you're looking for a general reaction scheme for a double replacement or double displacement reaction, you're going to watch for 2 compounds as your reactants. So I have some compound AB and some compound CD. Those atoms are going to rearrange to make something new, but again, remember that 2 positives can never go together, nor can 2 negatives. So I'm going to have to pair A with D. It's my only option to make something new and make sure that new thing is stable. Also, going to have to pair C with B. Notice that I wrote C first because C is the positive, and the positive always comes first in a compound. This is the general reaction scheme that you will see for a double replacement reaction. The last type is combustion, and combustion is just kind of its own deal. All of these other ones typically are comprised of ionic compounds. This is going to occur with covalently bonded compounds. So in a combustion reaction, we are the most familiar with these because we use these all the time. These involve fire typically. Something starts on fire. And in order to start on fire, we know just from our everyday lives that in order for something to burn, it needs oxygen. And that's true of any combustion reaction. So in a combustion reaction, we take something and we react it with the oxygen in the air, which is O2. The something that we burn is typically what we call a hydrocarbon. This is something that contains C's and H's. It could also have oxygens or nitrogens in there as well, but a combustion reaction will typically happen with C's and H's that react with oxygen in the air. The nice thing about a combustion reaction is that your products are always the same, guys. Every single time, you're going to end up with CO2 and H2O. Every single time. So let's look at an example of this. We can't really use our AB system of lettering here. Instead, what I'm going to do is start with something simple like CH4. CH4 has to react with oxygen in a combustion reaction. When that burns, it will always give off the same 2 products, CO2 and H2O, every time. Now, the thing that can be tricky about combustion reactions is the balancing. So if you are looking to balance a combustion reaction, my suggestion to you would be to list the atoms, but when you list the atoms, you always want to start with the easier atoms. These are the atoms that appear only once on each side of the equation. If you notice, my oxygen appears twice on the product side. That's going to make oxygen tricky to balance, so I'm going to put a little star here, and I'm going to save oxygen till the very, very end. I'm going to make my C's and my H's match first. So let's go ahead and start our count. We have 1 C on the reactant side, 4 hydrogens, 2 oxygens, and then on the product side, I have 1 carbon, I have 2 hydrogens, and I have 3 oxygens. Again, focus on C's and H's first. They're going to be easier to balance. Since my C's already match, I'm going to move to my H's. I'm going to put a 2 here, giving me 4 hydrogens. But remember that 2 multiplies all the way through. So I'm going to have 2 oxygens here in addition to the 2 that are there for a total of 4. Now that I've made my C's and my H's balance, now I'm going to tackle the oxygens. In order to make my oxygens match, I am going to put a 2 here, giving me the 4 that I need. That is now a balanced combustion reaction. If you are looking for an easy way to just identify your reaction types, you can pay attention to what your starting materials are. So your starting materials or your reactants can be a good indicator to predict your reaction type. Now, this doesn't work every single time, but for the vast majority of reactions, this will work. If you notice that you have an element and an element as your reaction, that will indicate always that it is a synthesis reaction. Two elements as a reactant, they have to come together in order to make something new. That something new is a compound. If you notice that you have just a compound, so only a compound on the reactant side, that's all that's there, that is going to indicate that we have a decomposition reaction. If we have an element and a compound on our reactant side, that is going to indicate that we have a single replacement reaction. Or again, single displacement is used interchangeably. If we are starting with a compound and a compound, that is when we know that we have a double replacement or double displacement. The one thing I want you guys to be careful of is your combustion reactions. Combustions will always have some number of C's and some number of H's reacting with O2. At first glance, it looks a whole lot like a single replacement reaction, but watch for that. If you know that going in, it makes it a little bit easier. As soon as you see CH, a CH-containing compound reacting with oxygen, this is going to be our combustion. My suggestion to you is if you think you have a single replacement reaction, just in the back of your head say, oh, you know what, I need to remember to check if it's combustion. You'll know it's combustion because if that compound is comprised of C's and H's and the element is oxygen, then you know that it's a combustion reaction rather than a single replacement. Well, I hope that helped clarify the difference between the different types of reactions and how to identify them. Like and subscribe and check out my other videos.